Hi, in the previous video we introduced the concept of Poisson regression and discussed many of its properties. In this video we're going to be performing Poisson regression with SPSS statistics and talking you through how to interpret the output that it produces. So the first example we're going to look at is in fact the data from the previous video that we looked at, which records deaths from horse kicks in the Prussian army in the late 19th century. And if you want to perform a Poisson regression, under the Analyze menu, you don't actually go to the Regression submenu. You go to this menu here, which is Generalized Linear Models, and choose the first item there, which is Generalized Linear Models. That will pull up this dialog with lots of tabs across the top. And the first thing we see here is we've got to choose what is the type of model that we want to run. Notice that you could do a linear regression here. You could do an ordinal logistic, a binary logistic if you so wished. But the one that we're interested in, of course, is under the count section here, because it's counts data, and we're choosing Poisson log linear. Notice that we have the alternative to Poisson if you got over dispersed data, which is the negative binomial. We touched on that in the previous video. So having chosen that, we then go to the next tab, which is the response tab, where we simply choose our response variable, if you like, or dependent variable, which of course is deaths from horse kicks. Everything else is grayed out here because it's not relevant for Poisson regression, so you can't switch anything on. If we go to predictors, in this case I'm actually going to just choose one predictor. I'm just going to choose cavalry corps here as a predictor. Notice that this is a category field, and because it's a category field, it's actually a nominal field with a number of different values inside it. As you can see, you can have all the different regiments, the different cavalry corps that people were in. There's 16 of them here or something like that. And we can send that across into the factors box. That's the relevant area for categorical fields. If you're familiar with logistic regression, you'll know that when you include a categorical variable, by default it chooses a reference category. So it's going to choose one of these cavalry corps as a reference category, and the coefficients are all going to be relative to that. In fact, it chooses the highest value, so everything's going to be relative to the 15th cavalry corps here, and that's what the coefficients are going to refer to. You can change it. You could say I can change it to descending order and say actually I'll have it choosing the first cavalry corps, which is simply labeled G. And then under model, we're going to click model here. We're going to choose which model effects we want to include. So we're going to choose, of course, cavalry corps. We're going to send that across. You could, if you had multiple variables here, you could define things like interactions, but we're just going to go for main effects at this stage. And it is a iterative process. So there, under estimation here, there are different methods that the parameter values may be estimated by. I'm not going to change any of those, but it's just worth noting that if you do get a warning message about it running out of iterations, hitting maximum number of iterations and maximum number of steps, you can increase those values here to get rid of those warning methods and allow it to regress to the final point where it's happy with the parameters that it's estimated. And if we go to statistics here, the only thing that's quite important here, it isn't included by default, is to remember to switch on include exponential parameter estimates. These create what are called incident rate ratios, and they kind of show the effect on the incident rate of each independent variable that's been added into it, or each independent term or category. So it's quite important. And then we have estimation of means, e-means. I wouldn't normally go for this, but I'm actually going to choose it here and send that across. It's going to do pairwise comparisons between the various cavalry corps to see which ones are statistically different from one another in terms of the mean incident rate, which could be useful. And then we have the ability to save, which I'm not going to bother with here, save out things like the predicted value of the mean response, and also to export the model out should you wish to reuse it again in the future. So having done that, let's simply click OK and have a look at the results. Click OK, and here are the results. You can see there's a number of different items that have been created here. We get case processing summary, we get information about the categorical variable that's been included. we get some goodness of fit statistics, we get an omnibus test, we get a test of model effects, and we get our coefficients table, and then beneath that we get our estimated marginal means and pairwise comparisons. So let's work our way through this step by step and just take a detailed look for our first example of running Poisson regression. Looking at the results in detail, of course, the first block of output that we encounter is a case processing summary, simply telling us that there were 280 records in the model. And that secondly, the categorical variable that we're working with here, the factor field, is cavalry corps. There are 16 different cavalry corps that were included, different categories, and each one of them contributed 20 records. The next block of output that we encounter, however, refers to the model itself. Now, initially, we've just shown some summary statistics about the dependent variable, reminding us, for example, that the mean incidence of deaths from horse kicks was 0.7, the minimum was 0, and the maximum number of deaths for a given regiment in a given year is 4. But beneath that, we're seeing the goodness of fit statistics table, and this table provides measures that are useful for comparing competing models. So although we don't see measures like R-square or pseudo R-squares here, we do have things like a log likelihood value, AIC and BIC values, and they help us compare one model against an alternative. A key statistic is this one. This is the dispersion statistic. It's the ratio of the Pearson chi-square to the degrees of freedom. And ideally we want it to be as close to 1 as possible, as this indicates that we have equidispersion, which meets a core assumption of the Poisson regression. Now, obviously, with this data set, we know that the dependent variable follows a Poisson distribution almost perfectly. So it's no surprise here to find that it is at 0.995, almost equal to 1. And when the value is notably larger than 1, it indicates, as we've said earlier, that we have over-dispersion. And this can be a problem because it can lead to the model underestimating the standard errors of the model parameters. In fact, later on, as we'll see, the output includes 95% confidence intervals of the model parameters. And that means that if the standard errors are estimated to be smaller than they actually are, the confidence intervals in turn will be narrower than they should be. On the rarer occasions that this value is shown to be less than 1, it indicates underdispersion, and the opposite problem occurs when the standard errors are estimated to be larger than they should be. And finally, we have an omnibus test here, which is simply testing the model against the fitted model against an intercept only model, intercept meaning the constant only. So it's just basically saying, is this an improvement on a model where we simply have a constant, an average added in? And it's saying that, yeah, if you add in the variable cavalry corps, it is statistically significant. It makes a difference to the likelihood ratio of chi-square value here. It gets a significant result. It's less than 0.05. It's not less than 0.01, it has to be said, but it's adding something to the model. Following the omnibus test, we have a test of the individual model effects, the two main components of the model, which is the intercept, the constant itself, which is shown to be statistically significant, making a contribution to the model, and the variable cavalry corps, which here again has a significance value of less than 0.05. After that, we encounter the parameter estimates table. And as per usual with these types of tables, the first parameter that we see is the intercept or constant parameter for the regression model. Here the parameter value itself is not the incident count, but rather the natural log of the incident count, as I think I mentioned in the first video. Poisson regression transforms the data into natural logs and uses a link function to convert the resulting predictions into the estimated counts. Notice that all of the parameters have an associated standard error, and this is shown in the second column. And it's this value which can be underestimated in the presence of over-dispersion, which in turn has a knock-on effect on the third and fourth columns, which show the associated confidence intervals for the parameters, making them unrealistically narrow. Now, we only had one independent variable in the model in the form of the factor term regimental corps. It's important to understand that all the values shown here are with respect to the arbitrary reference category of core 15. The values indicate simply that all but one of the corps see higher incidence of deaths from horse kicks, as denoted by their positive values, than the 15th. Only the 8th regimental corps has a lower average incident. Note also that only a couple of these regimental corps have significantly different average death rates compared to the 15th. This is the 14th corps and the 11th corps. In fact, Had we chosen core 0, labelled the G core as our reference category, due to its average death rate being around the midpoint of these mean values, none of the parameters would have been found to be significantly different from the reference category. But that doesn't mean that the variable itself doesn't make a statistically significant contribution to the model. And the third last column, labelled EXPB, which stands for exponentiated b, refers to the incident rate ratio of each parameter. And it provides a useful way to view the magnitude of effect each parameter has in the model on the incident rate in the dependent variable. Here it shows, for example, that the 14th core experienced deaths from horse kicks at a rate 3 times greater than that of the reference core of the 15th, whereas the 9th core's death rate was only 0.875 times that of the reference core. The last section of output refers to the marginal means table that we requested along with the pairwise comparisons. The first table here showing estimated marginal means. It's just basically a table of means showing us the average incident rate for each cavalry corps along with confidence intervals for those estimated means. And after that we see the pairwise comparison table, which allows us to compare the mean statistics for each cavalry corps against the remaining cavalry corps and to perform effectively a one-way ANOVA against that. You'll notice here that for cavalry corps G, compared to all of the remaining cavalry corps, none of the differences in the mean in the mean incident rates are statistically significant. They're all above 0.05. The same is true for the first cavalry corps, where none of them are statistically significant. If we look at the 4th cavalry corps, I've just zoomed in this one, you can see that there is a statistically significant difference in the mean incident rate for that corps compared to the 11th and 14th corps. And lastly, we get an overall statistical test just to tell us whether or not this field contains differences which are statistically significant at the 0.05 level. Here we can see that, of course, we've detected 2 already, so it shows that there are statistical differences within this variable when compared against the overall mean incident rate.